Hello everyone. Let's look at today's Leetcode problem 3405. Count the number of arrays with k matching adjacent elements. Before starting this problem, let us look at a motivational quote for today. All the water in the world cannot a ship unless it gets inside. Similarly, all the negativity in the world cannot bring you down unless you let it in. External pressure, criticism, all the doubt cannot stop us unless we are affected by the surrounding thoughts. Stay focused, protect your mindset, and do not uh, take any negativity from outside. That's how you stay afloat and move forward. Okay, so let us look at this problem statement. Uh, you are given three integers n, m, k. A good array of size n is defined as follows. So each element in array is inclusive of 1 to m. Exactly k indices I where 1 to n satisfy the satisfy the condition of adjacency. Okay, and within this range, return the number of good arrays that can be found. We need to return number of good arrays that can be found. Since the answer may be very large, return it in modulo of 10 power 9 plus 7. Okay. So let us look at this example. So let's say, so we know that length of the array should be, we need to consider length of the array as 3 length, and m is any element at I should be within the range m less than or equal to m and greater than or equal to 1. So this is the understanding with 1. And if k is equals to 1 means there can be adjacent pairs, number of adjacent pairs. Okay, so explanation. There are four good ways. So if you see, these are the four possible pairs that can be that can be built with the input for the string, and the output is 4. For example, at any point of time, we can consider 1, 1, 2, and let's say 2, 2, 1. That's another pair, and we can think about 2, 1, 1 as another pair, or we can consider 1, 2, 2, as these are the four pairs that can be considered, right? So let's quickly look at how we can solve this problem. So there are few things to consider. So number of pairs that can be formed in length of array n, maximum number of pairs that can be formed is n minus 1, right? So if we are asked to pick k such adjacent pairs, so if we are asked to pick k adjacent pairs in the array to make it as a valid, this is the point 2 I believe, and point 2, yeah, to have k adjacent pairs. So an adjacent pair consists of a minus 1 is equals to a of r. So this is the meaning of adjacent pairs. So if we we can calculate the number of pairs. Maybe I can take up a simple visualization example. Let's say we are given with n is equals to, let's say, 6. We would have 6 different items. Let's say m might be somewhere around, let's say, 5, and k is equals to 3. Let's say we can form pairs such as this: 1, 2, 3, 4, and 5. So we can form 5. We can form 1 pair, 2 pair, 3 pair, 4 pair, 5 pair. So the pairs will always be equal to n minus 1. So that's the understanding. That's what we can see. That's the first point. And next point is, if we are required to form k pairs, k adjacent pairs out of n minus 1, then our formula would be n minus 1 k, right? So yeah, so this would be our formula. It is a bunch of combination part where this can be equal to n minus 1 k factorial, k n minus 1 minus k factorial. So yeah. Yeah, so this is n minus 1 c k. So this is the value. And if we are required, so we know that this is the formula if we want to calculate, to pick k adjacent pairs out of n minus 1 pairs. So our next question will be, what is the values that we are going to fill if, let's say, n is equals to our n is equals to 6. Let me okay, so if n is equals to 6 and we have decided, we have calculated all the values with k adjacent pairs that are to be picked. So here we should be having this digit within the range 1 to less than this. A of I is equals to, let's say, if this is the array, then at this index, which is 0, 1, 2, 3, 4, 5, any digit will be less than or equal to 5 or greater than equal to 5. So it can be n possibilities, and all of these other characters can be, if these two are of a pair, then we might say this is also of the same digit and this can take up m factorial, right? Or these two will be equal. And similarly, if let's say these two are equal, then we can say that this should not be equal to this one, so it might be m minus 1 factorial, right? So same goes for this one as well. So m minus 2 factorial. So if we are considering it this way, uh, our combination of n number of ways to have a value at a specific index will be m ways, and it will be m factorial into m minus 1 minus k n minus k times 1 factorial. So this would be the whole point. So this is the number of ways we can place a specific digit at a specific character. Okay, so considering these two formulas, our result should be n minus 1 ck, and this part that we had m into m minus 1 n minus k minus 1 times and all of this mod by 10 power 9 plus 7. So this would be our final value, right? So there are few things to consider. If we want to solve this formula, we might exceed time limit exceeded if we are not using approaches such as, one is Fermat's theorem, and second one is binary exponentiation. So Fermat's theorem helps us calculate mod of a specific value where there is division also involved. So binary exponentiation helps us, let's say, a power n of this can be solved in times log n time complexity. So these two things, let us look at it. So firstly, if we want to understand the Fermat's theorem, so Fermat's theorem, let me just quickly, Fermat's little theorem. So this helps us calculate the remainder. Where, let's say, if a large value such as this is so let's say if we are given with a large value such as this, if we are needing to calculate remainder of this value, then we can do it this way with Fermat's theorem. So we can calculate 13. So let's say if we consider this as p, we 82 by p minus 1, 82 modulus of p minus 1 and divided by p. So this would be the formula. So in this case, p is 9 and this is 9 here. So 82 divided modulus of 8 will be 2 will be the remainder, and 13 power 2, 13 to the mod 2 will be, so if I need to calculate 13 power 2, uh, 169 will be the 13 power 169 by 8, then 16, 21. So 1 will be the remainder here. So this will be the output. So this way Fermat's theorem helps us calculate uh, a solution. So let's say a power k minus p minus 1 by p. So this will be the formula, and this will give us the remainder. Okay, so understanding this, and we know this would help us calculate modulus, while by the second part, which is binary exponentiation, let's say if there is a power 3 power 9, then we can say let's say this is a power b. If b is odd, then we divide it by 2, and if it is equals to 1, then we do it this way: 3 power maybe 4 into 3 power 4 into 3 power 3. So this would be our problem, where this would also be equal to 3 power 4 plus 4 plus 1. So yeah, and again this can be simplified by recursion. 3 power 4 can be 3 power 2 into 2, and 3 power 2 can be 3 power 1 into 3 power 1. So this can again further break down. Yeah, so understanding these, we can apply some solution. So let us go to the Leetcode editor and try solving this problem. So let us uh, write these two functions, com compute fact, and the first one will be complementary fact, where we send in two values n and r, and we need to calculate the combinatorics. Okay, this helps us calculate NCR, and we can send in values accordingly as we are sending here. And the next function will be calculation of mod power. So we are computing till the power of y is 0, and we are returning uh, all of the power values with mod being applied to it. So, and this would be next. Let's look at this function compute fact. So here, if we need to understand each part of the function, so firstly we are calculating all the factorials of numbers within this range, the maximum of 10 power 5, and we are calculating factorials from 1 to 10 power 5, and also the inverse, that is the n minus r, and r factorial also is being stored here, so that it can later come in handy here, as we see here. So inverse is equals to inverse plus 1 into gain plus 1. So yeah, this can be used to calculate the combinatory works here, as we can see, right? So with this way, we firstly calculate combination, that is first part of our selection of k adjacent elements in n minus 1 k pairs. That is the first part, and next part is uh, the m factorial, where we need to fill number of ways of filling a specific space with m values within the range 1 to m. So next one is with respect to m power uh, the m power minus 1 n minus k segments that we are considering to be filled with the values. So these two are separated in two lines, right? So both of these correspond to filling up a specific space with a specific digit of within the range m, and that formula would be m into m minus 1 power n minus k minus 1, right? So that's the formula that we are applying here, and each of these functions is doing its job, where combination we calculate the n factorial by n minus r factorial, as we see here, and we calculate factorials of we pre-calculate all the factorials within 1 to max, so that we can quickly make a lookup to get all the values. And next is finding uh, the specific power in exponential way, right? So this would be performing its operation in log of n times. So yeah, and these are bunch of variable declarations here. Okay, so let's try submitting the solution. Okay, so as you can see, the solution gets submitted. If we want to understand the time and space complexity of this solution, time calculation of binary exponentiation of power would be log n, while computation uh, of combination would take about O of n times, while this would take off O of n. So it would totally be, space complexity would be n plus log n, which would be n log n, and space complexity would be O of n, as we have uh, 10 power 5 values being stored in fact. Okay, so if you found this video helpful, please like and subscribe to my channel. Thank you.